Welcome everyone to day 2 of the EET 423 SCADA presentation. Last time we went over the high-level information as to what SCADA is, how it interfaces with P&C, as well as system protection. Today we're going to dive into the details and look at P&C drawings, logic diagrams, relay DMP data maps, and SCADA DMP data maps, and how they all work together to obtain a full functional SCADA system. This screen shows a simple SCADA system flow, and we're going to walk through each one of these individually. The physical interface we'll start with first, going into the hardwired inputs and outputs of the SCADA system and how that transitions to the relay and relay logic diagrams. And then from the relay to the RTAC or the RTU, the DMP data mapping that's utilized. And then from the RTAC or RTU to the SCADA system, how the SCADA DMP map gets utilized. Let's start with the physical aspect of SCADA. So at this point in time, no matter how many devices are set up in a substation to utilize some form of smart or intelligent communications, we're still left with a small portion that needs to be hardwired. This is typically your open and closed circuits, which rely on coils and mechanical machinery to physically move a switchblade or a breaker mechanism to impede or facilitate the flow of power. So let's look at a PNC control circuit of a motor operated switch to learn about the physical interface of SCADA. Okay, so let's start with the elementary diagram of a motor operated switch. This is the control circuit for that motor operated switch. What you'll notice is I've got clouded here a specific section of this elementary diagram, and this will be the section we'll mostly focus on here. The rest of it is PNC related. I've also got two devices over here that are highlighted. The information that I've got highlighted here on the screen is the physical interface portion of SCADA. So starting on the left here, we can see we have this DR device, which is your loss of DC aux relay. I grabbed a screenshot here of what a typical aux relay look like, just in case you guys are out in the field and notice one of these ice cube relays here. So it's got a pickup coil as well as some contacts that will go off to SCADA, and we'll show you that in the upcoming slides here. So just going over briefly how this loss of DC works is it's tied between the positive and negative DC rails, which picks up the coil and closes or opens contacts based on which one you're wired to, and sends that information to an input on the 2411. So if we were to lose DC, if one of these breakers here were to open, we would lose DC. The coil would drop out, which then would send the information or alarm to the 2411, and from the 2411 to the RTAC all the way to SCADA, so the control center can see that there is a loss of control circuit, loss of DC for the control circuit. Over here, something very similar, where we've got an aux relay going between the line and the neutral of an AC circuit here. So this is monitoring the loss of AC power for heaters. The section that we're going to focus on mostly here is this dotted box, which is the physical SEL 2411 device that we're going to be talking about here. So we can see that the device has a close and an open. These are output contacts, which the 2411 can physically open or close those contacts depending on the logic. And as you can see, the closed circuit comes down and hits the close coil, and the open circuit comes down and hits the open coil, which will then go off to the physical motor and apply power to one side or the other of the motor to either open it or close it. So we're going to skip to the next slide here and talk more about the 2411, but I wanted to give you a brief overview of what this circuit, the open and close, looks like. So jumping into the physical 2411, I've taken some screenshots over here to the right so you can see what an SEL 2411 typically looks like. This will be your front panel with some buttons on the right, some alarm LEDs, front port communication, and then going to the back of the 2411, we'll go into more detail about these, but these are your physical Phoenix block connectors that you'll connect your wires to. So right off the bat, we can see this elementary diagram for the 2411 is showing the serial port on the front, which I've got clouded and highlighted over here. We can see, and this is the card B for the 2411, has got ports 1A and 1B, which are your network ports, and there's a fiber coming out of port 1A going to a patch panel, which goes to your network switch for your communication interface to your station LAN. And this would typically also be shown on your COM block diagram to show the overall communication scheme and how this communicates back to the RTU. Just to highlight this, so here's your port 1 fiber interface with your LC ports. This is port 2. Currently, it looks a little different than port 1, but this is just a rubber cover that's been placed, plugged into this port so that there's no dust or dirt that gets into the optics on these fiber ports here. You can also see on card A, which is this card over here, we have A01, 02, all the way through A12. What we're going to focus on, again, are output 101, output 102, which are your open and close outputs from the 2411. If we go back a screen, this is exactly the same thing that we're looking at here. Here's out 101 and out 102, close and open. And going back to this here, we get the A01, 2, 3, 4, 5, 6, all the way to A16 down here. Something to point out is when you see this, this is a Form A, the open contact, and you've got a Form B, normally closed contact. And then also out 103 is special. It's a Form C output contact, which is a combination of your Form A and your Form B. Going on to the next page of the 2411, we are shifting over to the part C here, which are your, it's a combination of outputs and inputs. This 2411 is utilizing in 301, 302, 303, and 304. And as you can, if you can remember back to the first drawing, we had that loss of DC auxiliary contact, which was DR. We'll jump back to that. This auxiliary contact right here. So the coil would pick up, and this DR has extra contacts, which are 2 and 6, which wire directly into N304. So when the DC is healthy, N304 would be picked up for a value of 1 or true. And we've also got over here your 89A and your 89B. So from your ANSI standard device numbers, 89 is a line switch, and A is your Form A contact and your Form B contact. So the A contact follow your switch status. If the switch is closed, this contact's closed. the switch is open, this contact's open, and just the opposite here. So if the switch is open, this is closed, and if the switch is closed, this is open. And that again goes into 301 and 302 to give you your 89A and 89B switch status. We can also see in 301 there is a normal maintenance switch. This is a physical switch that can be utilized at the station if an operator needs to make sure that no SCADA controls are going to go through if they're physically inside the switch for safety reasons. They can put this in maintenance mode, which will cut off. Come back to this, they can put it in maintenance mode, which these will be open, and it'll cut off all the SCADA controls, so they know the only way to open and close this is with the physical open and close push buttons. Jumping over to the last slot, which is slot D over here. We've got a few more inputs. We've got the loss of AC power, the 89 ground switch, and the mech house door open. So all of this 2411 and heater and all the devices are in a mech house out in the yard, which has a door, and the control center wants to know if the door is open or closed.
Next section we're going to look at is the relay and its logic diagrams. We'll look specifically at the data that's produced by the relay that will be sent to the RTAC. Moving over to the logic diagrams. This is a typical logic diagram that you would see with inputs, outputs, and your IED logic. I'm not going to go into too much detail about all the functionality in here, as you'll get that in the system protection portion. What I do want to point out, though, is some specific logic information that is contained within the logic diagrams here. So I've highlighted these, and we'll reference back to these when we get to the DMP data map. Orange I've highlighted as control points. Yellow I've highlighted as binary status points, and in future slides you'll see magenta color, which are counters. So your typical logic diagram, on the left is your inputs and your right are your outputs. So these inputs can be physical inputs like your in 301 and 302 like we saw on the elementary diagrams, or they can be physical inputs directly from the 2411. So in this case, you can see this is a push button 01, which is your first push button on your 2411. So when you press the button on the 2411, this will pick up, and the same for push button 02, 3, and 4. These remote bits, the RBs, are generated from within the HMI in this case. So when you press a button on the HMI, it will send a control output to the 2411, which becomes an input to the 2411. So these are your software inputs, software control points. Internal here is your logic. This is a left to right flow of your logic from your inputs to your outputs. And I've got highlighted here some binary points that are going to be utilized within our DMP data map. These ones are specific to latches, a set and a reset latch. And then on the right side, you can see the outputs. Again, these can be physical outputs, as in the close and open strings, circuits that we saw on the elementary diagram. We'll get to that in a couple pages here, but right now you're seeing the TLEDs. So in this case, this TL1 LED is HMI disabled. These are your TLED lights on the left, so you can see the first one is HMI disabled. Your push button LED is the light on push button itself. And again, push button 2 LED for do not operate. Again, we've got we're looking at the motor operator logic from within the 2411. I wanted to point out again a physical input, so this is in 301. If we reference back to our elementary diagram, this is where our 89A physical contact came in into 301. So when the switch is closed, this will pick up, and internal to the 2411 in the logic, this point right here in 301 becomes high, and it will go through the logic as a logical 1 and hit your AND gates, your OR gates, your latches and resets, and perform logical operations in order to get the outputs. So again, in this case, in 301, we're going to be utilizing for your DMP data map in 302. You'll notice that some of these logical elements here are not highlighted, and it's information that's not necessary to the utility that this was developed for. Some utilities want all the information that's generated within a relay, and some utilities just want very specific information. So in this case, they want to know the 89A status, they want to know the 89B status, but they do not care if the users push the open push button or the close push button. Also in this case, you can see this is a logical element for a latch. When this latch goes high, LTO4 goes high. Within the DMP map, they don't care about this, so they don't care about the information that's generated from this to send it to an HMI or to send it to SCADA. On the next sheet here, we have our control circuits for HMI open, SCADA open, HMI close, and SCADA close. These again are remote bits. So remote bit 3 and remote bit 4 are generated from within the HMI, the human machine interface, from the operator pressing the open button on the screen. That will then send a command over to the 2411 through the remote bit 03 and enter the logical portion of the 2411 here. The next remote bits are remote bit 1 and remote bit 2. These ones are generated from SCADA, the ECC. So the control center operator will send an open command. It'll go into the RTU. It's sent to the 2411 via remote bit 01 and remote bit 2 and continue on through the logic to eventually open and close the switch. On the right side here, we can see the physical outputs. This is out 101 and out 102. These are the outputs that we saw in the elementary diagram previously that physically wired to the open circuit and the closed circuit to operate the motor. Again, we can see some logical elements here that are not highlighted and not important to the utility for the information that is generated. The next section is again dealing with your input 303, which is your normal maintenance input, as well as your 89 ground. Something to point out here is on your outputs, we had physical outputs or software outputs. One portion here you can see is an LCD display point. If we go back to the beginning screen here, this is the LCD right here, and this can display text. So when the in this case the counter when it counts up and counts down, it will hit the display point and visually indicate the counter for SC01. One thing I want to point out, this logic diagram again are logical elements that we don't monitor. So in this case, we're not monitoring push button 04 and we're not monitoring push button 03. The reason for this is this LED flasher. So this LED flasher, the logic for that is over here. It's generating an on and off element. So half a second on, half a second off, and it's doing that consistently. So if we were to monitor push button 04 and push button 03 within the RTAC, we're going to have a point that is going to be going high and low, high and low, high and low, high and low, high and low consistently, which is going to cause congestion in our communications when you've got a bit going high and low like that. So again, this is the basics of the logic diagram within the relay and how it relates to SCADA. Moving on to the RTAC and RTU portion, we're going to discuss the communication link between the relay and the RTAC, which in this case is going to utilize a DMP3 communication protocol. The DMP3 communication protocol, distributed network protocol, is a standard protocol used in the power utility world for IED to RTAC or RTU communications, as well as RTU to SCADA communications. And in order to map all of the information that we just saw from the logical elements in the relay to the RTAC, we have to use what's called an IED DMP data map, which will lay out the mapping between the relay and the RTAC. So let's get into that. So on the screen, we have a typical IED DMP data map for a utility. And we will kind of go line by line here, row by row, column by column, and just point out the major parts of the map. So first off, we have three different sections to this specific map. So we have the status and alarm data map, which is sheet 1. Sheet 2, we have the control point data map. And sheet 3, we have a counter data map. We'll jump back to the status and alarm portion of it. So the top part tells you the model or type of relay that we're dealing with here. So in this case, again, this is an SCL 2411. We have the RTU device name. So the switch is M201 and it's a 89 motor operator. And again, switch name 201. The heart of the IED map here is in this section here. This is where all of the information is laid out. So we have the relay element. Some of this is going to look familiar to you from the logic diagrams, and we'll jump back to the logic diagrams to show where that's coming from again. So TO6 LED, SV9T, SV10T, 11T, 13T. So if we jump back here, as I had mentioned previously, I'd highlighted some of these elements here for this portion. So we have TO6 LED, and that comes specifically from this portion of the logic diagram, so time sync fail. Next, we have SVO9T, 10T, 11T, 13T. So you've got your 9T, 10T, 11T, 13T here, and all the logic that's driving these points. The next column is the sheet number as to where all of these elements are derived from. So if you're working on the IED sheet and you want to go see the logic behind TO6 LED, you can quickly and easily see that it's on sheet 4. If we go back to the logic diagrams, we can see for the 89 motor operator, we have sheet 4. And again, we can find the TO6 LED and what's driving that time sync fail. The RTU tag alias, this is specific to the RTAC programming. If we bring up the RTAC code here, we've got our client, which is our 2411. And in our binary inputs, which is the status and alarm section, we can see that we have a tag name, which isn't very specific. It just says M201 89 motor operator binary in 000, 0001, 23. So this tag name is not too specific, but we have this column here for tag alias, and this is where we can define in easy to read terminology what this point is. So binary in 0 means nothing. But if we look at the tag alias, we can see this is the SNTP fail for M201 89 motor operator. This is the position trouble. This is the 27 loss of DC, cabinet heater loss of AC, and so forth. So the tag alias is just used within the RTAC code to make things easy to find when you're using them. The RTU logging on message and RTU logging off message. This is for SOE, which is sequence of events. So when one of these elements goes high or goes low, it gets recorded in a sequence of events. So, and timestamped. So when you're going back and looking to see why an alarm was picked up, you can go into the logging section of the SOE and see the timestamp as to when this went high and when this went low. And it'll also give you this naming here to let you know what happened. So logging alarm state is true. So this means when this element goes high is when we want to log it in the alarm state. So you can see that the on message here is trouble. So when this goes high, we want to say that SNTP server trouble. When it goes low, we say that the SNTP server is normal. And that is done within the tag processor in a logging view. We can see that we have all of our points laid out here with the tag aliases. And we've got our logging alarm state, which is a copy and paste from the DMP map here. So true, 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 and false. And then we've got our logging on message and logging off message, which again is a copy and paste from that IED map. So when this point goes high, because the logging alarm state is true or a high or a 1, it'll show a server trouble, and then when it gets low, it'll show a server normal. And again, with position, when it goes high, it's a position trouble. When it goes low, it's position normal. The relay word bit or alias again references back to the logic diagram. So TO6 LED, as we had seen before, SV09T. The next two columns here are where we get our mapping between the relay and the RTAC. So this IED sheet is kind of doing double duty. A&I team would create this IED map for the RTAC, but also has information in it that would get passed off to system protection in order to create the one-for-one mapping between the relay and the RTAC. So let's take a look in the relay configuration. So this is the actual logic for the 2411 And if we go down into the DMP maps under binaries, we can see over here on the right the mapping. So with DMP, you've got points 0, 1, 2, 3, and so on, all the way to 14. And we're saying on the relay side, binary in 0 is TO6 LED. Again, that matches up here. Binary in point 0 is TO6 LED. And they'll map that logical element TO6 LED to binary in 0. Same for binary in 1, SVO9T, 10T, 11, and 13, laid out exactly how this IED sheet is shown. So this creates the DMP map for the relay side. If we go over again to the RTAC side of things and we come up to our 2411 device in our binaries, we can see we have the same map laid out here, which is your DMP point index. So again, 0 is your TO6 LED. So point number 0 is our TO6 LED, and our tag alias, which came from this column, is added here for SNTP fail. So when the relay is communicating to the RTAC, we can now tell and make sure that when we send, or the relay sends binary in point 0, we know that it is the SNTP fail. Or if they send the binary in 4, we know that it's the door open or close status. The next columns here, so HMI screens, what this is laying out is every point that needs to reside on a screen. So on the HMI itself, if you go to a screen, we should see an LED for the SNTP server. We should see an alarm, an LED for position, trouble, loss of DC, cabinet heaters, loss of AC, and so forth. You can tell here that the 89B contact for the switch is not shown. The reason for that is the logic within the HMI only needs 1 point, so it uses the motor operated switch 89A status. So the image on the screen will open or close based on just this. So if the switch is closed, this will go high, and the image will show closed on the screen. And if this goes low, the switch will animate and open. So it's not necessary to bring this to the HMI screen. The next column is the alarm. So within the HMI, at the top portion of the HMI, there's an alarm section, and it's only text. There's no visuals, there's no animation. It just shows your active alarms. So we can see that within that alarm section, we're going to want to bring all of these points in whenever they alarm. The SCADA column here is the points that are going to be used to send to the control center for SCADA. This is the information that SCADA wants and needs. So you can see that they want all of this information, not to, they don't really need to know if the HMI control has been disabled on the 2411, not information that they need. That's not pertinent to the control center operator. And we'll get to this in the SCADA map portion of it and how all of this is utilized. I skipped over these checked columns here, but these checked columns are for on-site commissioning. So the A&I engineer will go on-site to commission this 2411, and they need to make sure that every single point here is correct. They need to make sure that when this point goes high, that within the SOE, it shows that SNTP server trouble showed up, and then when it goes low, they need to see that SNTP server normal was displayed, as well as the proper timestamp. And then along with this, they also need to see that it shows up on the HMI screen. If it does and it animates properly, they'll put an X in the checkbox. If it shows up in the alarm section, they'll put an X here. And then when they test to SCADA and it's properly working, they'll put a check here. So at the end of the commissioning for this 2411, every column that has an X here should have an accompanying X here to show that the A&I engineer did proper testing and confirmed it. And typically what you'll see on site when they commission it, every single point needs to be checked, and in order to show that, they'll highlight it. So this will show that relay element 0 is TO6 LED. It does show up on logic diagram number 4. The tag alias is correct. They saw on the SOE that yes, the text is correct. The logging alarm state within the RTAC and the relay word bit is correct. If the mapping between the relay and the RTAC come up properly, they'll highlight that. And then once they test this point, they'll put an X here. And they check it for the alarm section, and then when they check it for SCADA section, they'll put an X there. So in the end, at the end of commissioning, this entire sheet should be highlighted and X's should be populated in all the checked columns. Let's jump over to the control tab. So this is the information that comes from the RTAC and is sent to the relay. So we had mentioned previously on the logic diagrams, the remote bits. So this is, again, a bit that gets sent from the RTU, or in this case, the RTAC, to the relay. If we go to logic diagram sheet 3, we can see in orange, I've highlighted here, remote bits 1, 2, 3, and 4. 1, 2, 3, and 4. Again, on the RTU portion, the RTAC, if we go to the binary outs, we can see that the tag alias is motor operated switch open. We can see for point number 1, the motor operated switch close. So point 0 is open, point 1 is closed. And what you'll notice here in the control points versus, or the binary outs versus the binary ins, the binary outs have a few more tags associated with a single point number. So within the DMP protocol, within a control point, you can have an opera pulse, an opera latch on, opera latch off, opera trip, and opera close. And you can utilize these based on your specific configuration, as well as how the utility is working with their control points. The same relay to RTU mapping occurs here. So point 0 is RTU open. Point 1 is command from RTU to close. And then this is the command from the HMI to open, command from the HMI to close. So this is your SCADA open and close. We'll see that again from when we jump to the SCADA map, but the control center will send a DMP open point to the RTU. The RTU will then map that point to the relay on binary output 0. And you can see this, that the consumer is the SCADA portion of it versus the HMI open, HMI close. This is the local operator at the station pressing a button on the HMI to open and close the switch. And if we jump over to the binary output section, again, we'll see our DMP map 1 binary outs. We've got RBO 1, 2, all the way through 8. map to 0, 1, 2, 3, 4, 5, 6, and 7. And again, jumping over here, if we filter just for the SPS portion here, it makes it a little easier to see. So 0 is open, close, RBL 1, 2, 3, 4, 5, 6, 7, and 8. And as I'd mentioned on the binary status, the A&I commissioning engineer will do the same when they're testing this. They'll make sure that everything is highlighted, and when a point is tested and commissioned, they'll put an X, make sure that they can confirm that every point was properly tested to the control center. Moving over to the last sheet, this is the counter section. So this utility wants to know the number of operations for the switch, number of open and close operations, and it's only specific to the HMI screen. So the SCADA ECC is not concerned about the number of operations, but it wants to show it at the HMI screen. If we go back here, we can see in our counter section, we have the counter, which is SC01. Going back to the logic diagram, as mentioned in magenta here is our counter. So our SC01 is getting the total number of operation counts and sending it to the LCD display point as well as the HMI. Jumping over to the relay side of things, again, we can see SC01 is mapped to 0.0 for the counter. Moving on to the SCADA ECC portion, we'll look at a SCADA DMP map, which is the DMP mapping between the RTAC and the SCADA system. So what we have here is the SCADA DMP map. This map will be created by the automation and integration engineer, and this is the document that gets sent to the utility control center. And just like with the DMP map, the mapping between the relay and the RTAC, this document lays out the mapping between the RTAC and the control center. It's still using the DMP3 protocol. So as you can see, we're still using the 0, 1, 2, 3, 4 index points within the DMP3 protocol. Similar to the IED, we've got multiple sheets here. So this is the control points. We have the status and alarm points. And because the counter portion was not being sent to SCADA, we don't have a counter sheet. So the control points are the points that are generated from the control center and sent to the RTU. This is a full SCADA map. This is something that you'd see at a full station. So in this case, this would have 4 motor operated switches. For this presentation, we've only been looking at motor operated switch 201. So all the others are just they're redded out so that we can look specifically at 201. So we can see from the control center side of things, they only have control over the motor operated switches here. They don't have control over the normal maintenance switch. They don't have control over the HMI enabled, disabled, or anything. The only thing that the control center can control is the actual switch status. So we can see point 1 here is the map for the motor operated switch 201 open and close. And this map is identical to the map that is in the RTAC. If we go to the SCADA server EMP mapping, we can see that in the binary output status, we also have the 0, 1, 2, 3, and so forth. The logic that is behind those points in order to map it from SCADA to the motor operated switch, you can see that point 1, which again, DMP index point 1, is directly mapped to the opper pulse. So I had mentioned the different control points that you can have. In this case, the control center is sending a opper trip, and we are mapping it to an opper pulse of the motor operated switch. The opper trip is a quick pulse command or a quick on-off command from the control center. In this opper pulse, you can actually specify the duration of the output. So the motor operated switch takes a little bit of time to transition from open to close or close to open. So you can set the actual pulse duration in order to complete the full open and close. You can also see that within that binary output point or that control point, the SCADA has just one point. It's 0.001. But because of the control, they can send an opper trip and they can send an opper close, which then gets mapped directly over to your open or close of the 2411. So from the control center, they send a opper trip command coming into this this program here. You can see that the opper trip, it's mapped directly to the RTU motor operated switch point, which then again, using the IED DMP data map, gets sent to the 2411, which then utilizes the logic diagrams to send a control directly to out 101, which will open the switch. Moving over to the status and alarm portion. Again, this is a full station SCADA map. We've got red highlights here so that we can block those out and see just that we're dealing with the 201 switch. So again, DMP3, so we've got all of our mapping, 0, 1, 2, 3, 21, 31, 32, 33, and so forth. So from the SCADA, the control center side of things, they expect when they get a DMP point of 1, they expect it to be the motor operated switch open and close status. We can see that over here in the binary in portion of the SCADA map. We've laid out all of our binary ins, and our mapping here is showing that we are taking the 89A status and mapping it directly to the binary in 1 point to SCADA. This portion of the program, within this one line, it looks like it's mapping it 2 times, but the way that it works out is within a DMP point, you've got a .stval, a quality, and a time. So this SPS contains the value, the quality, and the time. And when you're online with this and you're viewing it, you can't quickly and easily see what that value is. So in order to help the automation and integration engineer when they're commissioning, we've also set up to the right here a mapping of just the .st val. So this is the actual value that we're seeing. It's either true or false. And when we go online with this, we can actually see if this is true or false because we're looking at the .st val. So it looks like it's double mapping it, but it's used mostly for commissioning purposes so that it's quick and easy to see if this binary in 1 is high or low. All right, so going back to the DMP data map as mentioned, so we can see that, let's go back to the status here. So we'll look specifically at the SCADA section. So these, this is the consumer, the SCADA consumer here. So you can see that the control center wants the SNTP server normal, position normal, DC normal, cabinet heater loss of AC. And if we look at the SCADA sheets here, again, we can see that here's our cabinet heaters loss of AC, or loss of DC, maintenance mode, control mode, status disagreement. So all those points that were shown on the IED SCADA map are directly linked. And let's take, for example, point number 32. So we need to take point number 32 is the status disagreement. So in the relay, if we find the status disagreement, which is the position trouble, we can see that it is relay DMP point 1, but in the SCADA map, going to SCADA, it is point number 32. So in order to show that properly, if we go to the position trouble within the mapping program of SCADA, we can see that SCADA map binary in point 32 is mapped directly to the position trouble through the tag alias. If we look at the 89 MO position trouble within the 2411, we can see that it is in fact that binary in point 1. So that mapping occurs here in this program where we take binary in point 1 and map it directly to binary in 32 to SCADA. As we talked about with the IED map, the commissioning, the automation and integration commissioning engineer will also have to make sure that this document is checked. So when they go and do, for example, the status disagreement, they'll have to make sure that the mapping to point number 32 is correct. It is in fact status disagreement. And when they tested it to the control center will need to confirm that in a true state, the disagreement was unknown, and in a false state, it was normal. The relay IED name tells you where it's derived from. So the status disagreement is derived from that 20189 motor operated relay. And again, the relay element or target is position trouble. So when the site is fully commissioned to SCADA, this entire document should be highlighted, and the IED portion of it should have a check mark next to position trouble to show that the SCADA portion was tested. All right, so we've stepped through every aspect of the SCADA system flow, from the physical interface to the relay to the RTAC to SCADA. I want to do is I want to walk you through an example that kind of combines all of those sections from the physical interface to the relay to the RTAC all the way to SCADA, as well as take a control point from SCADA and send it all the way to the physical interface. So stepping back to the PNC drawings, we're going to talk specifically about this loss of control circuit DC point here. So the loss of DC tied directly to your positive and negative rails of your control circuit. If we were to lose DC, this alarm point goes directly to in 304. So when we lose DC, this input 304 goes high. From within our logic diagram, in 304 reads that the value's high. It needs to be high for 20 seconds. This is a pickup timer. So if we've lost DC for 20 seconds, the SB10T relay element will pick up. Once the SB10T relay has picked up, it will get mapped to DMP point 2 of the relay. The relay will then send that to DMP point 2 of the RTAC. The RTAC then takes that and maps that to the loss of DC, which is point number 35 to SCADA. Now SCADA will display that loss of DC alarm on their HMI. If we take the example of the control point, so let's assume the switch is closed and the operator wants to open it. They will send a command to open on DMP index number 1. That command gets sent to the RTAC and it gets mapped directly to the RBO1 point, which is the RTU open command shown on logic diagram number 3. That RBO1 within the relay gets sent through the logic, gets sent out to out 101, which is your physical interface. Out 101 closes, goes into your close circuit. Out 101 goes to your open circuit and will hit your open coil, opening the switch. So that should give you the brief overview from your physical interface to SCADA and SCADA to your physical interface through your relays and RTACs. So that concludes day 2 of the SCADA portion of this class. In day 3, we'll take everything that we've learned in day 1 and day 2 and put it into the lab portion, which will do some hands-on with the physical RTACs, the physical 2411, the HMI, and we'll also do the SCADA portion of it. Thank you.